And we are live. Welcome, students, to our laboratory exercise for the week for Astronomy 1010. Today we are going to be doing the landscapes of Mars, or exercise number 10 in your lab book. I have included the landscapes of Mars handout in the Blackboard tab for lab number 11. This is lab 11. Also, I've included the Mars Mola topographical map. Mola stands for Mars Orbital Laser Altimeter. And it's basically a satellite with a powerful laser that shines down on the surface and measures the reflectivity. And by measuring the reflected laser beam, can get super, super detailed elevation information about the surface of Mars. Now let's ask the people that I can see here, did you guys open up that map on your screen? We can also kind of use my screen. All right, yeah, having your own might be nice if you want to look at it yourself. I, of course, can go to share screen with you guys. And once we're in share screen mode, you can see me scrolling through our topographical map here. Now, let's take a moment to talk about how this is going to work. In most labs, we have to measure some things and we have to do some calculations, but this lab is a little bit different in concept. What we're going to be doing is we're basically going to just walk through the lab. Some of you are asking, like, is it 10-1? It's kind of all of 10. It's the whole thing. And we're going to walk through these questions, and we're just going to talk about them collectively, and I'm going to have us write really, really short and simple answers. You can type the answers right onto the document if you have the ability to do so. If not, just mark them up in pencil and scan it or photograph it as usual, okay? But we're going to try to come up with real quick answers. And believe it or not, just walking through these questions and talking about them will help us learn a ton about the surface of Mars. So just follow along with the bouncing ball here and you'll see how this is going to work. Let's take a look at our map and let's take a look at our legend. In fact, you guys might even be able to just use my map the whole time. I think we can even share screens. You guys can draw on this or I can draw on this. So feel free to take over and grab the map if you want to ask me about something. But I think we should take a look at the elevation keys here. This shows us our elevation in meters as a color-coded bar. Remember that this colorful map is really great for seeing the different topographies of Mars, but actual Mars doesn't look like this at all. What, you guys know what color Mars is, right? What color is Mars?
Red.
Yeah, super, super red, right? Let's look at a picture of the surface of Mars together. It turns out there's a reason why everywhere you go on the surface of Mars, the Martian dirt, we can't say soil because we have not found any organic elements in it, but here's a picture from the Curiosity rover of a typical little patch of Mars. And you'll notice all of the Martian dirt is very, very red. And that's a result of what happened to Mars's water a long time ago during the geological death of Mars. Much of Mars's water molecules got broken apart by solar wind and ultraviolet light. And a lot of the oxygen that was once a part of Mars's water has rusted the surface of the planet through chemical reactions. And basically that means that the entire surface of Mars is red because all of that water evaporated into vapor and got broken apart by the solar wind. And I want you guys to notice something else here. Can you see these rocks on the surface of Mars? Can you tell me how they look different than rocks than you see on Earth? If you take a walk around your backyard or if you go hiking at Purgatory Chasm, you don't see a lot of rocks that look like this. How are these rocks different than Earth rocks?
Not as smooth.
Yeah, that's exactly what I wanted you to say. Thank you. They are not as smooth. Why not? Can you think of a reason why, Chris?
You don't have water erosion there. You only have wind erosion.
Yeah, these rocks are flinty and sharp and pointy like arrowheads. You'd almost never see such sharp, jagged. I mean, occasionally, but you don't just see every single rock sharp and pointy like this. Um, that's because Mars lacks any of that water erosion that we have today, which smooths out pebbles the way you see stones in a brook or something. Of course, we have a number of rovers on the surface of Mars. Curiosity, the Curiosity rover, is one of our flagship Mars rovers today. It's the most recent, well, one of the most recent ones. And it's basically like a tank on Mars. And I want you to look at how they designed the treads of this tank. You can see that they're not sort of airtight. They're like these tank treads with gaps in them because they have to drive over these sharp, pointy rocks. And the number one nightmare for the scientists controlling the Curiosity rover is that they will drive over one of these sharp, pointy rocks and break something or get the thing stuck. And then you'll have a multi-billion-dollar paperweight sitting on the surface of Mars. That would not be good. So in fact, they're so paranoid about driving over these sharp, pointy rocks that they only let this thing drive at like a few centimeters per hour. And I think they even drive it backwards. I forget what the logic was there. I heard it once at a talk, but they only drive it backwards and it's painstakingly slow. They give it a little command, a little push. They're just terrified of this thing getting jammed up. But this thing is a marvel of modern science. It has an imaging camera. It has all kinds of cool scientific instruments. It has a neutron gun that fires neutrons into the rocks to do spectroscopy and measure isotopes. It has drills that can take and analyze chemical rock samples. This thing is totally wild. It's a roving science laboratory. And it's currently in Gale Crater, I believe, where it's traveling around and drilling into the rocks, looking for signs that maybe microbes could have existed on the surface of Mars. In any case, I've been rambling here, guys, but the big picture that I wanted us to take away is if you look at the global surface of Mars, the surface of Mars all across the planet Mars, the entire surface, as you can see from this Wikipedia image, is red. And that's not exactly, Earth is full of these rich greens and browns. In any case, in our topographical map, the colors then are representing elevation. You'll notice where we see these dark purples, those are the lower elevations. And where we see these frosty white tips, those are the highest elevations. Now let's look around here. Where do you guys see the highest elevations on the surface of Mars? If we look at this entire map here, where do we see the highest elevations?
The volcanoes?
Yeah, right at the tops of these volcanoes here, right? And these are big boys. Mars has bigger volcanoes than Earth, including Olympus Mons, the largest volcano in the solar system. Okay, so another thing I want to point out is several times it's going to ask us to take a look at certain longitudes. You'll notice that they measure longitudes. Longitudes measure east to west. We have a set of black eastern-based longitudes and a set of red western-based longitudes. We're going to be using the red western-based longitudes today. So let's get right into it and see if we can answer a couple of questions. I'm going to turn on my Wi-Fi in case, I don't think I'm going to need my phone for today's lab, but just in case, I want to have it handy here. Okay, let's look at our first question together. The first question isn't really a question, so we'll just skip over that, and we'll go to question 2 together. And I want us to have a discussion here. You've probably noticed that the northern hemisphere of Mars is very volcanic, and the southern hemisphere is heavily cratered. Using the concept of crater density from today's class, which hemisphere do you think shows the older landscape, northern or southern? So here's the northern landscape here. It's some of these dark blues that you see, right? So this is the northern landscape. You see a few craters. When we go down to the southern hemisphere, you'll notice heavily cratered terrain, similar to the lunar highlands. So which would have the older landscape, the northern hemisphere or the southern hemisphere?
Southern.
Yeah. And that's based on what observation, Jace?
The amount of craters.
Yep, just as simple as that. So let's write that down. Okay, I gotta decide how I want to do this. Can I type into this thing? Because that would be kind of cute and convenient. Do I have? I'm not sure I agree with this font, but oh, okay. So, okay, boom. Short answer is what we're looking for here. Inspect the Mars globe or the map provided in class, and let's locate two basins in the southern hemisphere. The Aguirre Planitia is near longitude 40 degrees and latitude minus 50 degrees. And the Hellas Planitia is near longitude 290 degrees and latitude negative 40. These are easy to see in our map because they're labeled. So here's the Hellas Planitia over here on the right, and here's the Aguirre Planitia over here on the left. It says these two basins were probably formed by giant impacts of meteoroids. The smooth surfaces at the bottom of these two large craters are lava flows. Use the map and try to determine if you think the lava flows occurred before or after most of the heavy bombardment and cratering activity of the early solar system. So class, did the lava flows that make up the basins of these craters occur before or after heavy bombardment? What do we think? Anyone?
It's like after.
Yes. How do we know that, Jace?
Not as many craters. There's a few.
That's right.
But
This is kind of like the same story that we had with the lunar Maria, correct? They're much smoother than those craters. So let's type that in. After. And if we had to say why, and we want to keep it short and sweet, what would we say? We'd say the density of craters. Let's use some fancy $10 vocab words. In the basins, the density of craters in the basins is much lower than the surrounding highlands. And that's another fancy vocab word we can use, the surrounding highlands. I'll give you a moment to write that down. Huh? Okay, we'll go get it right after this. You guys got that? I'd like you guys to do a little exercise with me that might involve a ruler, okay? Or we'll see if we can do it digitally. I just want to check the chat here for anything. Is everyone cool? Everyone's got that stuff? Okay. I want to show you guys how to use these Mercator projections. Can you guys see here that there's kind of like a little key or a legend for how many inches or how many millimeters equals how many kilometers? It's like a scale factor. Can you guys see that it's, remember, Mars is a globe. It's a three-dimensional sphere. And the length you travel along a line of latitude is going to be different at different points in the sphere. You can see that here, right? Just a moment. Hold on, guys. Here's a piece of chalk. I just thought that I could demonstrate here. A globe, a map is a flattened out piece of a three-dimensional sphere, right? So, speaker view. The distance that you travel some centimeters along the equator is going to be different than the distance you travel at a higher latitude. Once you flatten this thing out, one of these, even the same length of line will artificially look, a northern line will look longer than the other one. Do you need the answer to the Y part of number 3? I think we did that.
Sorry, that was to Lucas because he was saying his laptop died.
Yeah, my laptop died. I'm sorry, right in the middle of you explaining it.
Oh, I see. No, that's fine. Talk amongst yourselves then. I I don't know if that was for me or not. Okay, sure, cool. All right. In any case, my point is these Mercator projections, we have to take a look at our latitude. Here's what I'm trying to do, guys. I want us to figure out how big is this crater. Remember we did this exercise with the moon? We had to figure out how big this thing was. Here the scale factor is already worked out for us. So let me see if I can do this. Can I make a line? Can I draw? Ooh, I got an idea. Let's use the draw feature, annotate, and let's draw a red or blue line across this thing. Ooh, this would be really cool. Now, this is so neat. Let's see if I can drag this down to my Mercator projection. What would you say the latitude is here? Let's slide along the edge. Well, first of all, I think it's around 40 degrees latitude. Let me just confirm that. Okay, so yeah, this is 30, that's 50, 35, 40, 45, 50. So if that's 40, I think that's about right there. Yeah, 35, 40. So this is basically 40 degrees latitude. So if I go to my annotate again, notice that this line covers the length of Hellas Planitia at this scale. And about how wide would you say the Hellas Planitia is according to this Mercator projection? Can you guys see that?
Maybe like 2,300 kilometers.
Yeah. That's pretty big, right? How would that compare to the United States? How many
Probably
kilometers?
3/4 of the US or something.
Yeah. It's close to 3,000 kilometers from coast to coast, right? So that's a pretty... Now, these impacts, they say, were created by giant meteoroids. Is that your everyday meteoroid, or is that your extraordinary meteoroid? What did you think about those impacts there? So 2,300 kilometers.
I
And
mean,
I think,
compared to all the other craters around it, it's way bigger.
right. And how often would we expect, all right, now I want to erase that line here. Annotate, eraser. Okay. Based on this lecture, how often would we expect a meteoroid of that, shoot, I'm sorry. I've got the wrong thing here. I think it's this
Is it
one.
like the once every 100 million years, or?
Yeah, that's what I was thinking too, right? Like let's say that the crater is usually 10 to 100 times bigger than the rock that hits it, right? So if that thing is over 2,000 kilometers, this thing was maybe 200 to 20 kilometers. And that's anywhere from once in a billion years to maybe once in Mars's history, right? But here's what's scary about the Mars Mola map to me. We don't have one of those impacts, but we have 1, 2 of these impacts, right? All right, here's the thing that I'm thinking, guys. At first, the story looks really simple. At first, it looks like, okay, we had a bunch of heavy bombardment, which made the highlands. And then as Jace points out, the basins are much smoother, right? So these things had to have formed after heavy bombardment. And yet that's also kind of a conundrum, because wouldn't it be weird that you just had a billion years of splat, 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 and then at the very end of the heavy bombardment, you get 1, 2 big whacks coming right on top of each other? You'd expect these things to be spread out in time by at least a billion years, but yet both of their basins are smooth. So that's a little bit of a conundrum. This is not as simple as it seemed at first. At first, it seems like basins are young, craters on the highlands are old. Let's take a look at this question and see if we can plug our way through it here. Using the Mars map, inspect the rim of Aguirre Planitia and Hellas Planitia. Look to see if the rims have more craters than the lava flows inside the rim. Look for evidence of ghost craters which have been filled with lava. Based on the appearance of the rims, which of the following historical accounts is most likely? Oh, shit. Oh, here we go. Okay. A, the giant impacts occurred early when most of the other impacts occurred and excavated the large basins with their surrounding rims. The lava filled the basins much later after most of the cratering activity was over. Or B, the giant impacts just happened to occur very late after most of the other craters had formed and the lava fills the basins immediately after their formation. Which answer do you think makes more sense?
I think A makes more sense.
I'm sorry, Tony, could you say that again?
I would say A makes more sense because giant impacts are probably going to occur in heavy bombardment.
Okay, just say that one more time for me, because the giant impacts are what?
Giant impacts are most likely going to occur in heavy bombardment, I think.
Yeah. Yeah. But we need some evidence, right? And I agree with you that A is the correct answer, so we'll circle that one. But let's take a look at the rims like it said. You know, the rim of a crater can tell you a lot about what's going on, more than you might think. Let's take a look at two different craters before we even get into that. Suppose I were to circle two craters here. Suppose I were to compare crater Dawes to crater Huygens. Can you tell me which crater is the older crater? If I compare Dawes to Huygens? Which of those looks younger and which of those looks older to your eyes?
Huygens looks older to me.
I agree, Kayla.
Yeah.
Why did you say that? So a couple of you say so.
I would say because of the cratering on Huygens.
The cratering inside or outside or?
Inside, Dawes looks a lot smoother. And it also looks taller to me.
Yes.
Huygens' rim is kind of deteriorated.
That I see that Jace is with me here. It's about the rims, guys. In the basins are both somewhat smooth with one or two craters each. But if you look at the rim really shows evidence of being beat up over time. There's craters along the rim. What else do you think has been affecting this rim besides cratering? Can you think of another geological process?
Erosion.
Yeah, this rim looks eroded as all hell. Whereas Dawes looks a little bit steeper and crispy, like Kayla said. So the rims can kind of tell you a lot about what's going on, even when the basins have similar levels of crater density. So let's go back down here and let's look at the rims. The rims are what seem to suggest that these giant impacts are actually old, because while the basins are smooth, the rims look especially beaten up by impact cratering along the edges. The ridges did suffer some heavy bombardment. Here's Gale Crater, where the Curiosity rover is currently located. And you might ask yourself why they would have chosen to drop their fancy rover in this place of all places on Earth. What does this stuff look like to you? You know what this reminds me of? It looks like aerial pictures of sand dunes. This looks like erosion, like maybe water flowed all through this thing at one point. You can actually see channels here going through the craters. So the rims look quite old, and that's what we're going to say here. We're going to choose A. Sorry. And for state what evidence used making this decision, we could say something like the rims of the craters show evidence. Hold on, let me see if I can make this box. You know what? I should do this not in this format. I want to stay consistent here. Let me use the eraser tool. And let me use the document tool. The rims of the Planitia show evidence of heavy cratering and erosion, suggesting that the impacts themselves quite old. Does that sound good to everyone? Okay, that's cute. Let's move on. Everyone ready to move on? Let me look at my peoples here. All right. Okay, I got those thumbs up. Okay, here we go. Look carefully at the crater density along the rim of Hellas and Aguirre. The basin that's older should have more craters on the top of its rim than the younger one. Does Hellas or Aguirre basin look older? What do you guys think? If we had to compare Aguirre to Hellas, which one would you say looks like the older one?
Aguirre.
Yeah, I believe that's a scientific consensus as well, is that Aguirre, it's a bit older. And not just the rim just looks like it's a little more beat up and deteriorated than the rim of Hellas. Aguirre, and for a Y, we'll state the rim of our Aguirre shows more deterioration due to impacts and erosion compared to Hellas. Wow, this goes a lot better when I'm typing it than when I'm writing it out on the board. You guys can actually do the same thing I'm doing, and if you can save this text, you can just email, you can upload the document right to it. This might be one of the ones where writing it out is more of a pain, but whatever. Just do whatever you're doing, and I'm sure it'll work itself out. All right, let's poke along here and see how we're doing. Most of the volcanoes on Mars look like mountains with a crater on their tops. Boo, that's not how we talk. What do we call the little crater at the top of a volcano?
Caldera.
That's right. Most of the volcanoes on Mars look like mountains with a caldera on their tops. These are not impact craters, but are instead calderas. Use Google Mars to estimate how many volcanoes. Oh my gosh. All right, let's try to go through this together. We're going to try to count the volcanoes. Here are the things that we're going to consider to be a volcano. Obviously, these big boys, which are Monses, are volcanoes. Anything that's a Mons we'll call a volcano. Anything that's a Tholus we'll call a volcano. Anything that's a Patera we'll call a volcano. So Mons, Tholus, and Patera are what we're going to look for. So obviously, for starters, we got the big boys, right? We got Olympus Mons, 1, 2, 3, 4 big volcanoes. Here's 5, 6, 7, 8, 9, 10, 11, 12. I've already got 12 over here. Let's keep poking around and looking for these things because we'll see them all over the place. I know there's a few over here somewhere.
Isn't Olympus Mons like the size of France or something? I remember
Yeah.
seeing something.
Yeah, it is. It's huge. I'll show you a comparison in a few moments. Oops, sorry, I'm on 12. All right, we'll call this 13. There's a bunch over here. 14, 15, 16, 17. If you look at the poles, you can even see some in the south poles. Oh, 18. There's 18. To the poles. Oh, wow. 19, 20, 21. You know, one of the first times I did this, I was just trying to, what are they getting at here? I think the point of this exercise is the more you look, the more volcanoes you tend to find. There are 4 big ones, but there's quite a few smaller ones that have been worn down over time. So I think our best answer for this, oh no, what did I do? What happened to my other window? Oh, here we go. Sorry, at one point they were connected to each other. Anyways, let's say about 20. So we'll use the tilde symbol approximately. Wow, it doesn't like tilde for some reason. Shift tilde. About 20.
It already says about.
Oh, yeah, good point. I just like using the tilde symbol, to be honest, and it just won't let me. tilde 20. Okay. Now, it wants us to list the names of as many of these volcanoes as possible. I think that's silly. I think what we'll do is we'll just write down the names of the 4 tallest volcanoes. Those are the ones you want to remember. Those are the ones on the Tharsis Montes plains. Olympus Mons, Escreas Mons, Pavonis Mons, and Arcia Mons. And rather than me writing them down, I want you guys to write them down, okay? So just list those 4 volcanoes, and I'll circle them here. Annotate, draw a box. We'll write down the name Olympus Mons, Escreas Mons, Pavonis Mons, and Arcia Mons. So can you guys just jot down those 4 volcanoes for me?
Why are they in a perfectly straight line?
That's a really damn good question that I was hoping you could tell me. Where else do we see volcanoes form in a line on Earth? Where do we see today in our lecture volcanoes forming on Earth?
Like in the Hawaiian
tectonic.
Yeah.
archipelago.
Yeah, in the Hawaiian archipelago. And what was making them form in a line? The Aleutian Islands are another example as well. What makes them form in a line? Come on, you guys know this.
So
Hotspot.
it's the convection hotspot.
Right, but the convection hotspot is doing it, but then what's the process that makes them actually form the line?
Movement of the plates.
Which almost seems to suggest that Mars had a little bit of what?
Tectonic activity.
Yeah, Mars actually tried to get its plate tectonics going. This plate was probably moving, and then as Mars's lithosphere solidified, the whole plate shut down. You know, one of the most interesting moments I had with one of my colleagues, Emily Burns, she's a geologist. And one day after lab, I was just hanging out, and I invited her to come in and kind of talk to me to get her opinion of all this stuff from a geologist point of view. And she said the most insightful things that I'll never forget. She said, look at how high the elevation is all around the Tharsis Montes plains. Like this must have been one big convective hotspot that was just constantly pushing up on the crust of Mars. You could almost see Mars's lithosphere just bulging up under the pressure of the underlying convection. Not only did it kickstart some little volcanoes and some plate tectonics, but I bet this Valles Marineris was probably a crack that formed, almost like imagine trying to burst out of a pie from the inside, just pushing up on the crust until it fractures. Of course, Mars doesn't have robust plate tectonics like Earth. So as its lithosphere cooled and thickened, the volcanoes sort of stopped forming, and you just have this kind of convection pushing up underneath here. It's almost like Mars is bulging right at this one point. Also, of course, all of that red stuff looks like past epochs of volcano flows, and we're going to get into that in some of our next bits here. Okay, so did you guys get the 4 volcanoes down? Can I not have to write those down? Okay, cool. This is an easy one. This is a giveaway. Using the elevation codes, identify the volcanic feature that has the highest elevation or the tallest volcano on Mars.
Oh, Professor, did we do number 6? I don't think I got it. Oh, okay.
Yeah, number 6 is about 20.
About 20.
Okay, I'm all good.
Okay. And then here we were supposed to write down, you know, Olympus Mons, Arcea Mons, Pavonis Mons, and oh God, how do I spell this? Escreus Mons. Did I do that right? Probably not.
ASCRAE.
AE. All right, I missed a vowel. All right. Whoops. Sorry. All right, number 8's real easy. Using the elevation color codes on Google Mars, identify the volcanic feature that has the highest elevation or is the tallest. What's that?
Olympus Mons.
That's right, Olympus Mons. That was easy. Okay, if you were to count craters on or near these volcanoes, would you be able to infer the age of the volcanoes relative to the surrounding plains? This question was always something of a mystery to me the first couple of times I looked at this lab, and then I slowly began to understand the logic with it, and I want to share it with you guys as well. If you were to count craters on or near these volcanoes, would you be able to infer the age of the volcanoes relative to the surrounding plains? So before I tell you the answer, why don't you just try to take a guess what you think the answer is? Let's look here. What do we notice about crater density in the surrounding plains and on the volcanoes themselves?
There's really few.
Yeah, very, very little. Although we can see occasional ones here. The real idea here is it's necessary to actually look at a high resolution image of Olympus Mons, and there's a beautiful one on the internet that's very super high res. I want to share it with you. This picture here from the Viking orbiter, there's a high resolution version, 2000 pixels. It's epic, okay? So look in there. What are you guys seeing?
There are like 3 craters.
Craters or calderas? Let's play a game called...
Some of them look like craters.
Yeah, let's play a game called Crater or Caldera to see what you guys can do. So let's start with, hold on, let me get my annotate out, draw. I want a fun picture. Let's use magenta, okay? Crater or Caldera?
Caldera.
Very good. How about the main one?
Caldera.
How about this one?
That looks like a crater.
I'm thinking Caldera because of the shape of the slope. How about these guys?
Crater.
Yeah. In fact, these are legendary. These here. Ooh, let's use cyan. These two are clearly craters. And these are a very important set of craters on Mars. I believe they're called the Shergoti impact sites. Did you know that 20 or so % of all meteorites found on Earth are identical to the surface composition of Mars, suggesting that giant impacts slammed the surface of Mars and blasted rocks in excess of escape velocity into outer space, where they went careening around the sun for several orbits and then eventually slammed down onto Earth? There's literally Mars rocks in the Antarctic permafrost. In fact, one crazy theory of life development on Earth is called panspermia, the idea that life actually might have originated first on Mars, and then microbes might have traveled to Earth, hitching a ride on a meteoroid that got blasted off the surface of Mars, which is a wild theory. And they think that the origin of most of those Mars rocks comes from these impact craters. Now, these impact craters, well, I think this one is 10 kilometers across, and this one is maybe 15 kilometers across. That means the objects which struck them were probably 1 to 2 kilometers. How often would a 1 to 2 kilometer sized rock be expected to strike Mars today?
Every hour or every day, roughly.
1
Oh, no, sorry.
kilometer.
1 kilometer. Sorry, I was looking the wrong one.
All right.
So every million years then?
If it was 2
Roughly.
kilometers, maybe even like every 100 million years, right? Let's say it's 100 million years between impact sites like this. What does it mean if I see giant impacts on the tallest volcano in Mars? What does it mean that the
Really
tallest?
old.
Yeah, or at least it hasn't erupted in how long?
100 million years.
Yeah, at least. And it's kind of cool. If you go to the wiki page, I guess we're on the wiki page here. They talk about the surface age. They've actually identified the surface age of Olympus Mons by doing spectroscopy on the surface rocks. And they estimate here, they talk about those two. Oh, by the way, you were asking about it being the size of France. There you go.
Yeah, there's a Nat Geo thing about Olympus Mons where they show that exact.
Also, look at the height of this thing compared to Mauna Kea and Mount Everest. I think Olympus Mons is an epic shield volcano. The slope is so gradual that apparently if you were to take a hike up Olympus Mons, you wouldn't even recognize you were on a hill because the slope is so shallow. It's hard to imagine the stupidity of this massive volcano, you know? Look how much taller than Everest it is. Somewhere in this wiki article, I won't spend too long looking for it, but from what I remember, they've estimated that the last eruption was something like 150 to 200 million years ago, which is about what you'd expect if you have those impacts hitting every 100 million years or so. Oh, here we go. Actually, crater counts from high-resolution images indicate that the lava flows on the northwestern flank range in age from 150 million years to 200 million years. So, what's the answer to that question then? The question that we were trying to answer, which is this question here. If you were to count craters on or near these volcanoes, would you be able to infer the age of the volcanoes? What's the answer?
Yes.
Yes. And for our description, our short worded description, we would say even 1 or 2 craters is enough to estimate the age of the volcano surface. Something like that. Just a short, quick answer. going to check to see how everyone's doing here. Okay, let's push forward. Inspect the area south of the Valles Marineris between longitudes 45 degrees and 100. Notice this area is not uniformly cratered or wrinkled. A boundary seems to occur at what longitude? Is the younger surface to the east or west of this boundary? So they're asking, this is the Valles Marineris, by the way. The Valles Marineris is like Mars's version of the Grand Canyon, but it's kind of like the Grand Canyon on crack. It's something like 14 times, yes, pun intended, 14 times longer and 17 times deeper than our own Grand Canyon. And they're asking us to kind of block out a region south of the Valles Marineris. By the way, not named after marinara sauce, but named after the Mariner spacecraft, which first imaged and explored it. And they're asking us to kind of block off a region south of the canyon between longitudes 145 degrees, which in the interest of time, I'll kind of draw out for you here using a box. They kind of want us, oh, let's undo that. They want us to kind of compare this zone down here. So do you guys see the natural boundary between two different planes that they're talking about? What's the boundary that they're referring to?
The red and white elevation to the yellow elevation.
Yeah, what's that structure called there? You guys, let me zoom in.
Dalmatia planum.
Well, I was thinking they were referring to this lump here, the Nectaris fossae. That's kind of the vertical boundary, right? Okay, so the way this works, let me just eraser that. And let me zoom out here. So the red stuff is the west and the yellow stuff is the east. What do you think looks older? The yellow plains or the red plains?
Yellow East Plains.
Yeah, I think the yellow stuff looks a little bit older as well. It's a little bit smoother in the red plains. So the younger surface is clearly to the west then. Oh, so okay, so this answer is west. What longitude is this at? We can estimate the longitudes up here. So it looks like we're going with western. This is 30 degrees. This is 60 degrees. What's each big tick mark worth? What is 30 divided by 1, 2, 3, 4, 5, 6?
5.
So 5 degrees. That means each one of these little guys is 1 degree. So this is 60 degrees. So if this is 60 degrees, I'd guess the Nectaris fossae is like 59, 58, maybe 57 degrees. Does that sound about right? Ooh. You guys got that? Look at the smooth plain named Tharsis Montes. Does crater density suggest that Tharsis Montes is older, younger, or the same age as the region south of Valles Marineris? In other words, they want us to now compare, shoot guys, hold on. They want us to now compare this region south of Valles Marineris to the Tharsis Montes plains up over here. Do the plains here surrounding the volcanoes look younger or older than the plains down here south of the canyon?
Younger?
Yeah, they're much smoother. So let's get that down. Okay, along the north rim of Valles Marineris is a place called the Candor Chasm rim. Locate this Candor Chasm rim. Does the area suggest that the canyon itself is older or younger than the plains to the north and the south? Let's take a look at the canyon itself. The Candor Chasm rim that they're talking about is a little hard to see in the picture, but it's this brain-like cerebellum structure at the top of the canyon. Do you guys think that the canyon is an old or a young geological feature? What's your best geology guess here? Is the canyon itself a younger or an older geological feature? What would you say, class?
Older.
Older.
Looks pretty
What's-
young to me.
I would say it's younger because it looks pretty well defined.
Yeah, and what's our number one indication of planetary surface age?
Erosion
No,
and crater density.
crater density. Do you see any craters inside the canyon?
None.
I can't see a single one. This must be a wicked young geological feature. In fact, to really get the sense of what's going on here, I want to show you guys a high resolution image of the Candor Chasm rim. Oh my gosh, there's this picture. It's so high resolution and it's so beautiful. It's this one here. I think it's 11,000 pixels. Let's get the really, really high res version. Oh my God, it's 9,000 pixels, yeah. All right, look how wild this structure is. Let's just zoom in there. Okay, first of all, here are the northern plains. And all you can see is splat, 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 crater, crater, crater. Now here's the southern plains, splat, 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 splat. But look, oh, look at this right here. I've never even noticed this guy. What's up with this crater? This crater has been chopped in half by, what the shit is all this? What's going on here? What kind of geology caused this? Almost I can see like some older craters that got messed up here. What geology caused all of this? What are these things?
Plate tectonics.
Maybe. Do you want to know what these structures look like to me? There are these things in geology called alluvial fans. This is an alluvial fan from Wikipedia. There are structures that have suffered some water erosion or something and literally just disintegrated the side of a mountain or a canyon. Here's another picture of an alluvial fan. That's what they kind of remind me of. Here's an alluvial fan. Can you guys see these pictures here? I don't know how they're showing up on your webpage. Here's an alluvial fan in Kazakhstan. Doesn't that kind of remind you of this stuff here? What do you think caused that again, Jace?
I said maybe plate tectonics.
You're not entirely wrong. Originally, the Valles Marineris was probably a tectonic-like structure, but something's been happening to this since then. And what the hell is that?
Water was running over it.
Oh yeah, this is like the telltale signs. Anywhere you see these dunes, water seems to have flowed all throughout this thing. This is probably carved out extra by erosion, both water and wind. And it's a very, very young surface if you compare it. Now, to add credence to Jace's theory about tectonics, do you guys see these structures down here? This is not a river. This is not a riverbed. You can tell the difference between tectonics and rivers because rivers have a kind of serpentine, like a windy structure, but plate tectonics have kind of a hard, jagged edge. This is stress on the lithosphere. This whole structure is probably being pushed up by underlying convection. So probably whatever formed this thing, Jace, was a combination of tectonics kind of forming a crack, but then water just flowing all through it and carving it out. So it's kind of like the Grand Canyon in a way, but it was definitely related to tectonics more than the Grand Canyon was. So let's go back to our question here. Do we think that the canyon is older or younger than the plains to the north and south? What was our final answer there? Students?
Younger?
Much younger, yes. Well, all right, we'll just say younger. Is there anything along the north and south rim that shows evidence of flowing water on Mars? Duh. Okay. Water flowed all through this canyon, forming alluvial, let's use our fancy vocab words, forming alluvial fans. I always like it when I can teach you guys a couple of fancy new vocab terms. Okay, we're moving right along. We're almost done, guys. Bear with me.
Wait, I need to finish writing. Right,
Sure.
just give me 1 second.
Take your
Sorry.
time. I'll sip some iced tea. That's what I'm good at. I'm just here to sip the iced tea, folks.
I'm all good.
Okay. Chris, how you doing? You good? All right. All right, let's move on. Look at the crater density inside Valles Marineris and choose one of the following historical accounts. Choose one of the following shitty historical accounts of the canyon's formation. A, the canyon formed before the surrounding plains, and the lava flows which made the plains did not reach the canyon. B, the canyon was cut into the rock by a river of lava from the nearby volcanoes. C, the canyon forms a boundary. What the hell? Lava doesn't cut into rock like water. Lava paves over stuff. That's a crappy answer. The canyon forms a boundary between two plains of different ages. Or D, the plains formed first and at one time covered the area. Valles Marineris forms later from an unknown cause. None of those are great, but which one is the least offensive, would you say? Uh-oh, Jillian. Cat interference. Cat interference. Cat crew's in the house. What do you guys think?
D.
I'd say D.
Yeah, I'll go with that too. D is probably your best. The unknown cause is probably tectonic in origin. Okay. Look at the area around the volcano Mons. Use a magnified image to locate several ridges or channels on the side of Mons. Make sure the channels were made by the volcano. Follow these structures to see if they extend out into the surrounding plains at its base. Look carefully for any evidence that Mons has been partially covered by another geological development. From this study, choose one of the following accounts. The volcano formed first and was later buried by a lava flow from another volcano. Or B, the volcano formed the plains from its own lava flow, and thus the plains and the volcano are the same age. Now, I want to show you guys a high-res picture, but first let's look at our map. Mons, you don't quite get what they're driving at when you see it at this resolution. So here's your picture of Mons, okay? And I believe that the channel they're referring to is this channel right there. Do you see that? But it's kind of grainy and it's kind of hard to see what's going on at this resolution. Luckily, the internet has a beautiful high resolution image of Mons in black and white that I want to show you because it's just absolutely spellbinding. Mons. Bear with me here. I don't know if they'll have it on. I don't like the one they. Oh, it's this one. It's the Themis image. And let's get the high res version. Oops, excuse me. I guess 2000 pixels. Yeah. Okay. Okay. First of all, this is a really beautiful photograph. It's pretty epic. And the first time I looked at this, I had to kind of do a double take to figure out what was going on. So we can see a very, very smooth main caldera here. And the first time I looked at these structures, I was kind of puzzled. I asked myself the question that we should always ask ourselves when we look at planetary surfaces. What type of geology caused this? What's your first impression, guys? What do you think? Which of our 4 geological forces caused this cool structure at the edge of Arsia Mons? Just throw out a crazy guess. You've only got 4 geological processes, so it's got to be one of those. What is this stuff? What are you looking at?
Volcanism?
Yeah, well, explain that, Chase.
Looks like a big flow of lava came right out that channel.
Yeah, which is weird because lava usually covers things over. Actually, the first time I saw this, Jace, you're smarter than me because I thought maybe this was once full of a big lake of water and that maybe water had flowed through, but it doesn't really seem to support that. The channels just aren't there. On the other hand, do you see how they form these long like tube structures? See how everything kind of looks like fingers around here? You see this at the top too. Look at those finger structures. These were probably calderas or side venting from the volcano blowing the edge out of its side. And then here's what happens. As you excavate the magma chamber, it becomes a thin hollow shell like a Fabergé egg or something. And the overlying weight of the basaltic rock just crushes and collapses the thing into something called a collapsed lava tube. We see these on the moon too, actually. Collapsed lava tubes. I love this phraseology here. You can see like a Martian lava tube or a lava tube on the surface of Mars in a variety of different places. I was hoping they'd have a picture. Here's a lava tube in Hawaii. Look at this. This was once full of lava. Now it's excavated itself. And if too much rock sits on top of this thing, it will collapse it. And let's go back to our internet picture of collapsed lava tubes. You can see them on the surface of the moon. You can see them on Earth. This is on Mars. I was hoping to see one on the moon. Anyways, if you look at pictures of collapsed lava tubes, oh yeah, here's some structures like that. And pretty much, I think that's what you're seeing here. I think these are all eruptions that blew off the side of the volcano and then, yes, did spill some lava out onto the surrounding plains. So which of the answers to those questions then is our best answer here, A or B? This should be easy, right?
B. Would it be B?
And we'll just keep it nice and simple. Why do you think so? You can just say, I spy. Oh, shoot. Hold on. This is the wrong text bubble here. I spy collapsed lava tubes. Okay. I spy with my little eye some collapsed lava tubes. Okay. I think that's the last question I need for us to do. Okay. So that, I'd say that about wraps it up. Oh, I will mention one last thing here. I just on, rather than actually answering these questions, if you want to look at more cool stuff from the surface of Mars, you guys may know this already, but there is such thing as Google Mars, just like there's Google Earth. And what's kind of cool about Google Mars is you can explore the surface right from your internet browser and not only go all around Mars and see the global topography, but you can click on structures and you can see high resolution images and photographs like some of the stuff that I showed you today. Obviously, some of the things I've showed you today are a small patch of the surface on Mars. For instance, if we click on, one of the questions wanted us to click on sand dunes, and you can find where sand dunes are located on Earth. Where do you guys see sand dunes being located? I'm sorry, on Mars. Where do you see the sand dunes? Are sand dunes scattered randomly around Mars? Or is there some logic to where I see those sand dunes? I can actually just click on a structure here and I can get some cool high resolution images. Oops, sorry, normally you can do that. Dunes, let's look at this dune right here. Oh, bloody hell. Well, I'm doing something wrong.
What's
Hey,
up
by
with
the
that?
Yeah,
What's up with that big cracked area near the 3 Mons?
here, this.
Below that. There.
Oh, so cool. This is something called the Noctus Labyrinthis. The Noctus Labyrinthis is an area of Indiana Jones-like channels that are located right where the Valles Marineris connects to the volcanoes. And I'm so glad you asked me that question, man, because the Noctus Labyrinthis is just one of the most beautiful places on Mars. I want to show you a couple of wiki pictures from it. So here's a high resolution image. Wait, no, there's a better one of the Noctus Labyrinthis from space. I want to show you this one in particular. This is actually something I meant to bring up during this lab, and I was about to forget it. So you did me a solid here. Tools, size, large. One picture in particular. There's just a beautiful, beautiful photo. There's two that I want to show you. I can't believe it's not the first image because it's so, all of these are cool images, but the one in particular, this one. This is the picture that I wanted to show you guys. Look at what this looks like and try to imagine what it would be like to spend some time down there in the Noctus Labyrinthis. Where'd this go? Okay, here we go. Do you guys see how the bottoms of the canyons are all white? Any idea what that might be, all that white stuff? That's all carbon dioxide. That's dry ice. Mars's atmosphere, as you'll learn next class, is mostly carbon dioxide. That's all frozen carbon dioxide frost all along the valley of the Noctus Labyrinthis. Imagine walking through this. This would be like a network of Indiana Jones channels covered in this cool white dry ice. The reason I'm telling you this is because at certain times of the year, the Noctus Labyrinthis will get warm and that dry ice, that CO2, will sublimate into frost. And then the Noctus Labyrinthis becomes like the solar system's coolest fog machine, okay? And I want this picture, but as a higher resolution image. One of these images should show fog, yeah. And this is from the Viking image. Do you see that? This is also the Noctus Labyrinthis, but that's all full of dry ice fog. So if you were to walk through these canyons, you get this super cool fog machine effect. And all of that fog blasts along the rock, and it actually carves out those channels from wind erosion. So Jace, the reason why your question is so cool is because that's an example of frost jets or wind erosion on Mars, which is one of the things I was hoping to talk about. So that can be a perfect description or discussion that makes up for those last two questions. Okay, so at this point, I'd say that we've answered all of our questions, and you guys can now just simply submit that document, and that will be your 10 points for lab. Thanks so much for asking about the Noctus Labyrinthis. I really, really love that feature. Are there any questions from the class? No? Okay. Well, hopefully you're all staying safe and not going too crazy, cooped up in your houses. Weather's getting nicer, maybe take a walk. maybe they'll start reopening businesses again, and we can all go out for a drink at the bar.
Stop drinking wine at home.
Huh? Yeah, stop drinking wine at
Stop
home.
drinking wine alone at home.
Yeah. Okay, great to see all your faces. So, Tony, you and I can have like a chat or a private Zoom or something so we can figure out what's going on. Chrissy, nice to see you. Nice to see everyone. Ernie, I'm glad you're with us today. Oh, Matthew has some questions. What's up, buddy? Ask away. Your audio's weird today? No problem. Just type it up and we'll answer. Maybe everyone else can benefit from that too. Oh, you missed a few questions of the lab, you're saying. Is that right? Okay, can you tell me which ones and I can show you? I can show you those dudes. I don't think, everyone make sure, oh, please make sure you submit the lab to the proper lab number 11. Otherwise it gets really messy for me to grade your stuff. I graded all the homeworks and labs last night, so check your numbers and make sure you got some points for everything. 3, 7, 17, and 18. I don't think we did, 17 and 18 we don't have to do, okay? So don't worry about 17 and 18. I chose that our discussion of the Noctus Labyrinth is better than that. As for 3 and 7, 7 was just the name of the 4 tallest volcanoes: Olympus Mons, Arsia Mons, Pavonis Mons, and Ascraeus Mons. And number 3 was the density of craters in the basins is lower than the density in the surrounding highlands. So hopefully that answers those questions. Oh, sorry, was I just sharing my screen with you? I guess I wasn't sharing my screen, was I? Once again, Matthew and anyone else, here's question number 3. After and the density of craters in the basins is much lower than the surrounding highlands. And questions number 7 was just the name of the 4 tallest volcanoes on Mars. Does that take care of your needs, Matthew? Where's that chat? That's after. Okay. All right, guys. I'll stop the recording now. Yeah, Samantha, see you Wednesday. I'll stop.